Okay, people, let's continue. Okay, people, let's continue from where we left. Last time we started talking about minimum edit distance. We said that this is a example problem that uses dynamic programming. It is simple, very simple to explain, to at least what the problem is in terms of the definition of the problem. It is simple, and the solution is a trivial application of dynamic programming. So that means it's a good candidate to start to see what kind of NLP applications we are going to deal with. That's why we started doing it. And the nice thing is this is about words, and this doesn't involve much linguistically related knowledge. That's why we started talking about it. The idea was, if somebody types in something like this, we know that it is not in the dictionary. So he must mean something else. Is it this one or this one or this one or this one? So each of these is a regular valid word that can happen in a dictionary. So we have to choose one of them. Usually the one that is most similar, the one that is the cheapest in terms of keystrokes, changing from this word to one of these, is the one that we are going to pick. So we like to pick the minimum edit distance solution. When we say minimum edit distance solution, the most obvious edit distance is erase all the characters, 1 2 3 4 5 6 of them. Okay, erase all of them and add these 4. That means 6 plus 4, 10. And between these two, edit distance could be 10 if I do it that way. But I like to find the minimum edit distance, not the edit distance, arbitrary edit distance. So what is the smallest number of keystrokes that I have to use to change this word from this form into that form or the other form? That was the problem, and we said that this problem is not only specific to natural language processing. Many other areas of engineering and sciences using, for example, computational biology, they try to find the two sequences. What is the alignment between these two sequences? Says that if I am giving these two sequences, some of the letters are the same, some of them are not. So which letters should I drop and which letters should I insert so that these two can be matched? That's another problem that can use this information. In NLP world, this kind of solution is used for machine translation, information extraction, speech recognition, etc. Okay, we talked about this last time and we stopped after that. Let's continue our discussion, and let me skip all these. And I think this was the example that we were using. Somebody intention to execution, what is the minimum edit distance between them, and we kind of calculate it as 8 because there is one deletion, then 2 substitutions. E is going to stay the same, 1 insertion, and again 1 substitution. 3 substitutions and 3 substitution, 1 deletion, and 1 insertion. That's the cost, and we are going to calculate this cost 8. Okay, so there are many other applications of it. As I said before, let me try to get rid of whatever I have written before. Okay, and we said that this minimum edit distance can be found using a regular state space search, but the space would be too big, so we don't want to do that. we like to find some other solution. So minimum edit distance is the dynamic programming based minimum edit distance is going to work like this. I am given two strings. One is x of length n. The second one is y of length m. And we define a two-dimensional array dij. Okay, this dij will give us the minimum edit distance between x and y, but it will give us all the minimum edit distances of the subwords of x and y. Okay, that means the first I characters of x and the first j characters of y. So it's going to be like a table. It's going to be like a table. Okay, and in this table, okay, this is going to be D11 and this is going to be D and M. D11 will give us what is the cost of minimum edit distance between the first two characters of the given strings. That's the idea. Okay, so we are going to do it with the dynamic programming. Okay, we are going to compute each element of the D and M. When we reach this part, the upper right corner, then we are done because we have calculated all the distances and we have calculated the two whole words. So when we are calculating all of these numbers inside this matrix, okay, we are gonna solve. It's like, remember our example, execution to intention, or just the opposite. First, we are gonna solve this problem. Okay, what is the minimum edit distance between these two words, E and I? It is very simple, just one substitution. Okay, just one substitution, or one deletion, one insertion, or one insertion, one deletion. All of them, their cost is 2, right? Because substitution is cost 2. After I calculated the distance between E and I, then using those values, then I will calculate what is the distance between these two words, EX and IN, in. Okay, and I know the distance between E and I. On top of it, I am gonna do some calculations and I will find the distance between these two words. Then I will continue, and then maybe I will find the distance between these two words, exe and int. Okay, that's the idea. And we are gonna say that doing this all the way to the completion of the words, we will find the minimum edit distance between these two words. Okay, so it's a bottom-up building strategy. We will compute dij for small ij, and for compute the larger dij based on the previously computed small values, and we will be done that way, and we will hopefully reach to this position D and M. Okay, good. Okay, let's look at how we are going to do that. Remember, this is our, maybe use a different color. This is our table. Okay, this is 0 0. I said 1 1. Okay, but we start from the 0 0. 0 has a meaning, and we will see it. And it says that for the initialization, fill in all the row zeros and column zeros with INJs. So it's going to be 1 2 3 4 5 6. It's like that, right? Let's say this is execution Okay, so 6, 5, 6, 7, 8 and 9, and here I have intention in 10, whatever. Okay, I didn't have enough space, but okay, this is what it says. 1, 2, 3, 4, 5, 6. So this box here 1, 1, this box here 1, 1. Okay, what is this one? One is, let me put this sharp sign here. Sharp sign means null. Okay, one is the cost of converting a null string to a E. Okay, one is the cost of converting a null string to an E. 2 is the cost of converting a null character, null string to EX, right? And 3 is the converting, you got the idea. How about this one? What does this mean? It means that converting an word I to a null string. Okay. This 4 means converting this int, okay, to a null string. That's the cost of it. I can calculate this very easily because all I'm doing is insertions and deletions. Initialization is easy. And then this is the second part. In the second part, as you see, I will change all the i's from 1 to m. For each I, then I will change j's from 1 to n, and I will do this calculation. It says that to fill in a box like that one, okay, look at 3 things. Okay, what am I going to put in here? You're going to look at this value. We're going to look at this value. Okay, this value is the, again, cost of converting a null to an E. That's the insertion. Okay, so on top of insertion, if I do a deletion with a 1 plus cost, then I can convert this I to an E. So it is going to be 1 plus 1. Okay, so I can put a 2 in here. It could be a 2. This one says that, or maybe you can maybe start here. You just start from an I. Okay, you can start from an I. I is a word, okay. It means that, this one means that you started from a null, okay. You started from, you started from a null. You started from I, okay. You just deleted an I because I am null, okay. And now you are inserting an E, okay. This is again plus 1. One did the deletion, one did the insertion. The other one says that maybe just use the substitution, okay. Come from the diagonal and do the substitution. Just convert I to E. The substitution only happens if E and I is not the same. E and I is not the same. So I will say that, okay, the cost of substitution is 2. So again, this one is 2. This one is again here. It says that take the diagonal 0, 0. Okay. Its value is 0. By the way, this one is 0. The address is 0, 0, but the value is 0, 2. Okay. Take the diagonal. If these two are different, then put a 2 in here. If these two are the same, then you're going to put a 0 in here. Okay. You don't add anything. Okay. Somebody has a question?
Yeah. You said like number 2 means converting null character to X. So by that you mean D0 to D0 to index at the table is the cost of changing a null to an X, right?
If you go that way, okay, you are inserting something, Okay, if you go this way, you are deleting something. Okay. And if you go that way, you are substituting. Well, this means that you had an I at the beginning. To go from I to null, that's the cost of matching I to null, right? So you are going from I to null. So you have to spend just one keystroke. If you are at this situation, that's the cost of I. What would be the way of getting an E out of this? So you deleted something, you are inserting something in there. So then if you do it that way, okay, so this is delete and insert. This is insert and delete. Okay. If the row is up, it is delete. Arrow is up, it is delete. Okay. This is insert. This is substitute. Using these three operations, okay, if you keep doing this, let me do this. If you keep inserting, you reach 9, right? Then you keep deleting. Okay, you deleted all the intelligent words. Then you find some kind of a distance between these two words. But I don't want to do that. This way is too long, okay? Because you are doing the most stupid thing, deleting everything and inserting it, or just the other way around. I don't want to do that. I don't want to find the shortest path between this position and that position. And that's going to depend on the contents of the words. Okay? Maybe this example will make it even clearer. Let me find the example from the book. Yeah. Okay. So let's look at this again. Remember, this is our formula. Formula says that, okay, for this one, I need to check this one, that one, and that one. Either I am going to add 1 to this one, or add 1 to this one, or maybe add 0 or 2 to this one. Okay, so let's calculate. If I come from this position, that means that if I am coming from here, I inserted an E to, what does this mean? I made a null string an E. I inserted an E, right? So how would I convert an I to an E in this case? I know how to make a null string an E that way. If I just delete an I in here, okay, in that case, I would convert an I to E. So the cost of deletion is 1. So if I come from this position, it is 1. If I come from here, it's going to be again 1. But if I come from here, it's going to be 2. Why? Because these two are different. So it doesn't matter where I come from. Okay, these are all 2's. So 2 is the cost of converting an I, the word I, to converting an E. Let's look at this one. If I come from this place, again it is 2 plus 1, 3. If I come, it is 2 plus 1, 3. How about this one? Is it going to 1 plus 2, right? Again, this is 3. Okay? And it goes like that. Let's go to interesting places. Let's go to, how about this one? Tell me what would be the cost of this one? Tell me the cost of this one. It is either 3 plus 1 or 3 plus 1 or 2 plus 2 or 2 plus 0. Is it 2 plus 0 or 2 plus 2? Somebody said something? Yes, it is 2 plus 2. Ubaydullah says, I guess. It is 2 plus 2. Why? Because E and I is not the same, right? E and I is not the same. So it is 4. I guess it goes like, then this one is 5, 6, 7. Now this is interesting, yeah. Okay. Let's look at here. 7 plus 1 is 8. 7 plus 1 is 8. How about this one? Is it 6 plus 0 or 6 plus 2?
7.
It is 6 plus 2 or 6 plus 0. It's going to be 6 plus 0 because i's are the same. See, these are two i's. I don't have to, so substitution works very well. Okay, so I'm going to use a substitution, but I am going to use a substitution like this case. Okay, 0. Xi and yj is the same, so it's going to be 6, right? Okay, so that means that converting execution like this one, not to converting this 1 2 3 4 5 6 7 letter word, converting an I to a 7 letter word. I am keeping just I and delete and inserting all these execution stuff. How about this one? What am I going to write in here? What am I going to write in here? I would write, somebody said 7. Why is it 7? Because 8 plus 1 is 9. 6 plus 1 is 7. Is it 8 plus 0, 7 plus 0 or 7 plus 2? Of course it is 7 plus 2 because O and I different, so it's going to be 7. Okay. And I think this is going to be 8. Let's fill in this part. This is going to be 3, 4, right? Yeah. And this is going to be 3 plus, okay, this is 3, right? Because e's are the same. And it goes like that. And I keep filling this table with this idea. Here is going to be, I guess, 4. Here is going to be 5. This one is going to be 5 again. This one is oh, okay, is there a 3 here? 3 plus 1, 4. 4 is going to be 4, right? No, 4. Am I doing something wrong? No, I don't think so. Is this the same? Yeah. This is 3. Yeah, this is going to be 4. And it goes like this, and let me show you a filled in stuff. I think it is doing exactly what I am doing. It says that, what am I going to put in here? Either 1 plus 1 or 1 plus 1 or 0 plus 2 or 0 plus, yeah, okay. So I did that and I found that okay. I found that it's going to be 2. And it goes like that, and it looks like they filled in everything, and at the end I have 8 in here. Remember, we already did that, but this one makes a guarantee that you cannot do anything better than that, because while I am doing this, I tried all the paths. Okay, I tried all the paths. How would I convert this intention to this execution? Okay, so this 8 tells me the minimum edit distance between these two words. but it doesn't tell me how many substitutions I should do and how many deletions I should do, how many insertions I should do, because all I did was calculate which one is smaller and which one is same, and etc. I did not keep information of where I came from. I mean, this 8 looks like, why is this an 8? It is an 8 because I guess because of this 8, because n and n is the same. If they are the same, then it is not 9 plus 1 or 9 plus 1. It is 8 plus 0. So I came from here. It looks like I came. So it looks like they changed the color of this nice path. Okay. I will follow this path to find which way to go. So it looks like first start from 0, from null to null. First delete I, right? Delete I, then make a substitution with en n, then another substitution tnx, then just skip because substitution works, then insert a c, then another substitution, substitute n with u, then substitute, but letters are the same, t is the same, I is the same, O is the same, and n is the same. Okay. So, but I mean, I don't want to keep guessing where I come from. Okay. I mean, this is nice in terms of finding the minimum edit distance, but I like to know what should I do. So in this case, okay, I need to do some backtracing. We need to do this by backtracing, where I came from. Okay. Every time we enter a cell, I remember where we came from. So when I do this, you remember what I did here? It is 2. It is 2, but did I come from here or there or there? So just choose. It didn't matter in this case where I came from. I would say it is here. Okay. It's going to be 3 here. So I'm going to come from here. 4 here, right? 5 here. And 6 here. It goes like that, okay? So I keep that information where I come from. And when I am at 8, 8 will tell me that I come from here, okay? 8 will tell me that I come from here, okay? At the end, I will have something like that. So this one says that it didn't matter where I come from there or there or there, okay? Okay. If I follow this one, I will find all of my edit distance cost and edit distance path. Okay, any questions? Any questions about edit distance? It might look trivial for you, but if the words are very, very long, like 200 letter words, by 200 letter words, it becomes complicated, as we have seen in the case of computational biology example. Okay, so this is minimum edit distance with backtrace. And when you do the backtracing, of course, you need to keep a pointer. Where is your pointer, left, down, or diagonal? Which one? You choose one of them. Okay, good. So the distance matrix is this one. A path from this lower left corner to upper right corner. we need to find this path. If you look at this path, the cost on this path, okay, the numbers on this path is non-decreasing. Non-decreasing means it has to either increase or it has to stay the same. Non-decreasing path. Okay. And it's an optimal path. To go to this 8, you have to pass through this path. You cannot do any better than that. There cannot be any other paths going to 8 because this is the shortest one, or because this is the least costly one. Okay. Also on this path, what is the meaning of 6 again here? How would I? Okay, the meaning of 6 is this. Let me close all the rest of the. Can I do that? Okay, let's do, instead of that 6, let's look at this 7 in here. 7, this 7. What is the meaning of that 7? 7 is the cost of converting this word intent to exec. Okay. Converting that intent to exec. Okay. And you cannot do, you say that you cannot do better than that. Okay. You cannot do better than that 7. Since I know all the optimal numbers in my problem, all of them, using these optimal numbers, I can make my job easy for each step to calculate the next phase of the dynamic programming building table building. Kıvanç has a question. He says that what makes moving right insertion and moving up to deletion? It's something that I have decided. I mean, you are not asking what makes the diagonal substitution, right? Because our job is converting this intention to execution. Okay? If I move up, the meaning of 9 is you need to delete 9 characters to get to null string. So moving up is deleting one character. Moving right means that inserting one character. One here means that converting a null string to a E. 2 means, okay, converting a null character to EX. And 8 here means that converting an intention to execution. That's my definition. I designed the whole thing, and I designed it that way. Okay. So if there are no questions, let me move on then. With the pointers, I can know where I am coming from, and that's fine. Okay. Every non-decreasing path from 0 to 0, 0 to mn is the alignment. Okay. And an optimal alignment is composed of optimal sub-alignments. Okay. With these sub-alignments, I can put them together and find the optimal alignment. That's the idea of dynamic programming. And we're going to do this over and over again with the dynamic programming. We are going to do this over and over again. It works very well with one-dimensional problems. This is a one-dimensional problem because I am matching just 2 one-dimensional strings. It works very well. And the nice thing about is, what is the running time of this algorithm? What is the running time of this algorithm in terms of big O notation? Yes, exactly, nm. Okay, because there is a loop in here, right? That's the runtime requirement O N M. And for the space, I think how much do I need for the space? For the space, okay, it's a two-dimensional array, and M again. So linear in terms of the number of letters in X and Y. Okay. Just a minute. I need to take this one. Sorry, I'm sorry. Efendim? Merhaba. Okay, sorry for that. Again, for the space it is an M, for the time it is an M. Very nicely behaving algorithm actually. It is linear time in terms of characters. Okay. And I got the alignment, yeah. For backtracing actually, all you need to keep is the arrows, okay, between the optimal ones, and it is N plus M. But it doesn't make much difference because I am already spending n times n place. Okay, so weighted edit distance is something that people use in many places. We don't say that the cost of replacing an e with an I is the same as cost of replacing z with an x, because I mean it is possible that since z and x are very close to each other on our keyboard, it is possible that when I am typing it, it is likely that I am confused between them. Okay, depends on your keyboard and etc. So some people said that let's give weights to some substitutions, okay, and let's modify our minimum edit distance algorithm accordingly. This is some statistics for English text, and they tell you how many times I made an error between one character to another character. Sub xy, substitution of x for y. X is incorrect, y is correct. So if somebody typed here, E, okay, 388 times, he meant actually A. C and A are mixed together a lot for some reason. C and O again, large. What is the largest number in this figure? I am seeing 388, C and A, right?
It's E actually.
Sorry, yeah, E and A, yeah. So both vowels. So people are confused, either misspelling error or they are just typing it wrong. I think it's just they don't remember the letter right. M and N, They are very close here. M and N, they are very close on my keyboard. It kind of explains it. So this table is not calculated using some kind of a program. It is just a statistics. Okay. You let some people type English text on keyboard. After that, you find their misspellings and see which words are confused with which words. These are the substitution costs then. So how am I gonna change my algorithm then? In that case, instead of adding 2 or 0 to this case, okay, I am going to add it with some substitution cost. Okay, if the substitution is not very likely, its cost will be higher. Also, I have this deletion and insertion cost too. In this table, I don't have the deletion and insertion costs. Okay, I mean, deletion and insertion costs are just single one-dimensional arrays. Substitution cost is two-dimensional. These are one-dimensional. Okay, so this is weighted mean minimum edit distance, and for this one, it is language specific, and it might be even person specific. Okay, it might be even person specific. Good. Okay, any questions? Okay. You might wonder why they are calling this dynamic programming. This thing was invented in 1950s. Somebody named Bellman, this guy, he invented it. Okay. He said that he didn't want to use anything mathematics or research because they had very difficult time to get funding. Programming was very positive words those days, and he just picked them. So dynamic programming doesn't mean anything actually. It is not about programming. It is not about dynamic. He just calls it dynamic so that the name is interesting. Okay, good. If we come back to this computational biology example, okay, I like to match this word with this word, very, very large words, and this is the result. Again, the problem is the same. Some insertions, insert a T here, okay, keep A and G, delete a G, okay, and delete these two, make a substitution, delete these two, make a substitution, insert these two. Again, this is the minimum edit distance between these two. Very, very useful. Very, very useful. Okay, so they do this in computational biology to find the important regions that are matchable. Okay, and uncover evolutionary forces, determine their function, etc. And this is a very popular algorithm in there. Okay, so I think I am not going to talk much more. Yeah, maybe I should talk about it. I should talk maybe about this too. Sometimes important thing is between these two words is the center part. You want to ignore the beginning of one word, and you want to ignore the ending of the other word. Okay, so you don't want to penalize gaps at the ends. Ends of the words are not important for us. The important thing is in the center part. So how am I gonna find the center part? I mean, what if the ends are so short? So how am I gonna do this? How am I gonna do this? So this is what I do. Remember our initialization? It used to be I and J, right? So they say that don't do that. Don't do I and J. Instead, do 0 and 0. Okay? Do 0 and 0. In that case, all the costs of, by the way, in this case 1 is here, okay, and M is here. No, is that correct? No. Yeah, M is here. Okay, so these are all zeros. These are all zeros. That means that if you like to go anywhere from here to there is possible. So I can do from here to there, right? I can do that. So ignoring the beginnings and ends can be handled by doing this. Okay, overlap detection variant, like that. Anyway, I don't want to go too much details into this thing. There are many things. Sometimes we can do this kind of stuff in the beginning, in the middle, and in the middle, etc. I don't want to go into that kind of stuff. Okay, these are not that much related to what we are doing. So that's it for the edit distance. Your homework number 1 will be about the edit distance. Your homework will be this. Start working on it. Let's say I typed a word. Okay, this TSY. Okay, and I like to find the minimum edit distance between this word and all the words in my dictionary. Let's say I have 100 words in my dictionary. One of them is test. The other one is I test, etc. Okay, so I like to find the minimum edit distance words so that I can pick one of them. So if you like to do that, maybe you can run this minimum edit distance. Let's say this is 100 words, 100 times, and pick the smallest edit distance word. Or maybe you can do is use a three-dimensional table. Okay, M and N. Each word is a z dimension in the. Okay, this is test. This is I test. This is O test. This is test, etc. Okay, don't fill in the whole volume, but start filling in from this corner. Okay, start from this corner and fill in this corner. If one of the words are getting too expensive, then don't continue that. Okay, first find all the words that can be substituted with a single substitution or insertion or deletion. Then 2, then 3, then 4. Continue this until you have enough number of words to offer to me. You say that, okay, I found 5 words that can be substituted, inserted, deleted using only 5 strokes, etc. Okay, so your homework will be this, and I will try to explain it in homework. Okay, it looks like I am out of 50 minutes. Let's take 10 minutes of break, and after the break we will continue. Any questions about the minimum edit distance? Or okay, no question. Okay, let's be here 15:01. Okay.
Hocam yarın sen ne kadar zaman ihtiyacın var? Ben şeye başlayayım. Learn Profile. Yoksa sen hepsini kullanır mısın?
1,5-2 saate bitirin. 1 saatin kalır zaman. 1 saat.
Saat yeter mi ki? O zaman 1,5 saat var.
Ha?
1,5 saat bırak bana.
Tamam.
Ben o zaman seni uyarayım, şeyde bitir. Ara verirsin herhalde.
Bitmeyebilir ama ya.
Bitmez mi? Ya işte bitmez o zaman ben yarıda kesmem gerekecek. 1 saat yeter mi bana bilmiyorum. Yetmiyor biraz. Bu sefer biraz daha böyle rakamlarla oynayarak.
Ben kestim, sen de kes.
Tamam öyle yapacağız. 7 kişi vermişler projesine.
Tamam.
Kızdım. Gördün mü bilmiyorum mesajımı.
Görmedim, yok. Hocam şimdi derse başlayacağım.
Sen derse
konuşup. Okay. That was a minimum edit distance. Oh, by the way, let me get my attendance. I took the attendance. Okay, so let me start another topic. This one we are going to go into more details of morphology. But before we start studying morphology, maybe just a reminder, maybe for those of you who are not that much familiar with the finite state machines, we'll talk about finite state machines, okay? Finite state methods. They are very easy actually. Regular expressions, they use them a lot, and we are going to use them too. Regular expressions are like, for example, I like to find the word the, okay, or I like the word to find the, but the first letter could be either lowercase letter t or uppercase letter t, or before the there should be a blank white space, and after the b there should be a white space, etc. These are all regular expression stuff, and so most of you know about this, and we are going to use these regular expression stuff a lot in our finite state automata. Okay, basically we will do this. We are going to use finite state automata, okay, to make morphological analysis of words. Okay, morphological analysis of words. What do I mean by morphological analysis? A word is not a... Okay. Can you find this word in Turkish dictionary? When you look at this word, you find this word in the dictionary, right? Masal-like story, you find it. How about this one? Can you find this word in Turkish dictionary? No, because this is inflected form. You put an affix at the end of this word, root, stem of the word, and you make a token. And although you see many times this kind of word in the text, it doesn't happen in the dictionary. So I need to do the morphological analysis of this word. I should say the root is masal, okay? That's the root, that's the noun, okay? And at the end, I put a suffix, okay? I put an affix at the end of this masal to make it masale. So what is this I? I is sometimes used for accusative form, ihali, right? Sometimes it could be accusative. Sometimes it is for iyilik eki, right? Masalı, onun masalı. Sometimes I use it for the iyilik eki, so it is who owns this muscle kind of ethics. So that's called morphological analysis, and we are going to do the morphological analysis with the finite state machines. Finite state machines are very simple actually, and to show them how they work, let's look at this example. Let's look at this sheep language. Sheep language, koyun dili, is very simple. Okay, you either say ba exclamation mark or ba or this or as many times as you like, right? But it always ends with an exclamation mark. In English, the sheep make a sound of ba, okay? It is not me in Turkish. They speak a different language in English. Okay, and this is our finite state machine that recognizes a sheep word. Q0 is the start state. It has to start with a B. When it sees a B, it comes to Q1. Then when it sees an A, it comes to Q2. When it sees an A, it comes to Q3. Well, it looks like this is not a word, right? This is not a good sheep word. This is a good sheep word, right? So I need at least two A's. So B, A, and then if I see the exclamation point, I reach this Q4. Q4 is the final state. Why do you call this final state? Because it is double circled. This is the start state. Okay, and these are my states. There are a total of 5 states, and these are the transition rules. Okay, we started making fun of that using the sheep language, but later we are going to do it. Okay, so I'm trying to read your good. So this is finite state automata, and this is the graphical representation of it. Okay, it has 5 states. Okay, in its alphabet there are B, A, and exclamation marks, and that's it. That's the whole alphabet. Q0 is the start state, Q4 is the accept state, and it has 5 transition rules. If I am in Q0, then I get a B, then I'm going to Q1. Okay, another machine that recognizes exactly the same language. I mean, this one and this one, they look different, but they recognize exactly the same language. What is the language? It is either BAA, right, or BAA exclamation BAA exclamation, etc. Okay, and the thing here is that it's kind of weird here. When it is Q2, if I receive an A, this one says go to Q2, this one says that stay in Q2. This one says that go to Q3, this one says that stay in Q2. So there is some kind of a issue there, but we are going to look at it later. That's something we want. Formally, mathematically, when you define a finite state automata, okay, you give the number of states, okay, the set of states, in this case Q0 to Q4, alphabet, in this case A, B, and exclamation mark. A start state is Q0. There is a start state, a set of accept or final states, in this case Q4. It's a set. There could be more than one accept or final states, and the transition function that tells you what should happen when I receive an input from one state. Okay, so alphabet is, I mean, don't take the alphabet as like A, B, C, D. Sometimes it means other symbols like the exclamation mark. Sometimes complete words could be your alphabets. Here is a finite state automata to recognize written form of dollars and cents between 0 to 100. So if you like to say 21 dollars and 50 cents. Let's say if I can recognize this, okay, I started from Q0. When I'm at Q0, if I receive 20, okay, where is 20? Here is 20. I found 20. So that means that I am getting this this transition. I started from Q0, then I went to Q1. Pardon, no. I went to Q2. Okay. 20.
Actually, first we need to go to Q1, I think. Under the line.
Yeah. There is another 20 there. If I come to here, Q2, and when I look at the next available transition, as input I have 1, I cannot do anything. That doesn't mean that I should stop and reject the string. It means that, okay, there could be other solutions. So I try the other one. So from Q0 to Q1, I try this. I come to Q1 and I input 1 here. I come to Q2, 21, and with the dollars, I come to Q4. I have reached a final state because there are 1, 2, 3 final states. I have reached a final state, but that doesn't mean that I should accept the string yet because there are other parts of the string. I mean, when the string is, I am all finished up with the string, I should be in a final state, okay? Being on a final state by itself is not enough. So I am at Q4, $21. It looks like there is no end between there. Okay. $21. And after that, 50 cents. There are 2 50s. One is here. The other one is here. Okay. I have to try both. Okay. If I do this one, come to Q5, then cents doesn't happen. Maybe I should choose the other transition. So get 50, go to Q6. Okay. After Q6, cents comes and Q7. When I'm at Q7, it's a final state, accept state, and I am done with all the string. So this is a finite state automata to recognize if written form of dollars and cents expressions is valid for English, sorry. Okay, very toy example, but it works. I use this for recognition, but I can use the same thing for generation too. I mean, just start from here, follow the things, okay? From Q0, okay, just choose this one. I'm going to do the, okay, 40, and then either choose that one or that one, dollars. Choose this one, 30, choose that one, 9, and choose that one, cents. So $40, 39 cents. So it's a valid expression again. So I use this to generate a valid English expression. Okay. So finite state automata could be used for this kind of both generation and recognition tasks. Very convenient. And I'm going to use it for morphological analysis. Okay. This is our transition table that corresponds to this finite state automata. If you are at Q0 and if you receive a B, you go to, okay, if you are Q0, if you receive a B, you go to 1, Q1. If you are at Q0, if you receive an A, then it's a reject. No, I cannot go anywhere. Okay. If you are at 0, and if you receive exclamation mark, you don't go anywhere. You just don't, you should not receive it. Okay. Good. Okay, this is our finite state automata transition table. Remember, there are formally states, alphabet, start state, except final states, and the transition function. That table is our transition function. It's a 2-dimensional to 1-dimensional. Okay. For each state, you list all the inputs, and for each combination, you define a destination state. Okay, good. That's how we do the recognition. That's how we do the recognition. Actually, this is finite state automata and finite state machines are very much used in the theory of computation a lot. They were invented by the early theorists of the computer science. Turing has said this. He said that, let's say I have a tape, a very long tape. On tape, I have my inputs written in each cell. Okay. When I start from Q0, when I start from Q0, input is A. I go to Q, I guess, was it Q1? I don't know. I think, let's say it is Q1. Q1, and now my input is B. Then I go to that, and my input is etc. and etc. So this tape approach was there from the beginning, and people sometimes use this to show the similarity between this and the early proofs of the computer science. Okay, so, and this is the general algorithm. This algorithm takes the tape and the machine. Tape is this input tape, okay, and the machine itself is the 5-tuple thing. It is set of states, our alphabet, and start state, final states, and the transition table. If you take this, it's a state, it's a machine, and tape is our input, and it executes this machine on this input, and it turns either accept or reject. Okay. So when do I return reject? Reject happens here and here. This one, the first one, the green reject happens if current state is an accept state. Oh, okay. So tell me when the green reject happens, and tell me when the blue reject happens. Question. When does the green reject happen? When does the blue?
The input is end, but we couldn't reach the accept state.
If the input is reached, but the current state is not an accept state or the final state, that's true. And the green, the blue one happens. There is input, and I am on a state. When I read the input, my transition table doesn't give me anything. It is empty, right? So it is then reject again. So I know it says that, as far as I remember, there is an invalid state for. No, the invalid state doesn't have to be there. Sometimes they put sometimes they put an invalid state, and whenever I mean, see, these are empty, right? These are empty. Let's say this invalid state is, let's say, state number 5, Q5. All the empty places are fed with this, with 5s, right? That's what they do. And whenever that reject situation occurs, it goes to that invalid state. An invalid state does something about it, but this doesn't have to be there. Okay, sometimes engineers do that. Okay, blue reject invalid state. It's not an invalid state, it is just I don't have anywhere to go, so I am rejecting this string. We don't have invalid states in this formalism. We don't have to. Sometimes it helps, but we don't need that kind of practical solution. Okay, so the key point is derecognize is a very simple algorithm. All it needs is the machine defined like that and the tape. It runs, it either returns accept or reject. And accept happens only once, this blue accept. Okay, the input is finished, there is no input, and I am on a accept state. Okay, and it is universal for all unambiguous. Oh, okay, let's look at this one. What do they mean by unambiguous regular languages? Well, sometimes there are languages, regular languages, that are ambiguous, such as this one. For example, this one. This one says that if you are on a state 2, if you receive the input A, you can go to either 2 or 3. Which one? I mean, it says it doesn't tell you anything. It just says that you can go to 2 or 3. Okay, it is your responsibility to make sure that you try all the paths. Okay, you don't say, okay, let's look at this one, B A exclamation mark. Okay, when I get the B, I go to, okay, Q0, then Q1 when I get the A, and another A at the beginning. Q0, I received B, Q1, I received A, Q2, and I received another A. I can stay at Q2 or Q3. Let's say I decided that I go to Q3 again, Q2 again, Q2. Okay, now I am receiving an exclamation mark, but that Q2 exclamation mark doesn't make any sense. Does that mean that I am rejecting this according to the algorithm that I showed you? Well, the algorithm that I showed you doesn't work for this kind of finite state machines, because this is ambiguous. Why? Because I have two solutions. For this kind of finite state machines, you have to try all the paths. If this didn't work, you go back. Instead of going Q2 here, maybe you should go to Q3. And in that case, if you go to Q3, then you are at Q4 and you're done. Okay, so this thing only works for unambiguous regular languages. For the ambiguous regular languages, well, the solution is not that difficult, but it is different. Okay, so the key points: translating the regular expression into a machine table and passing the table to the string to an interpreter is good enough for us. Okay, so sometimes they prefer doing this as a state space search, but I don't want to go there. And we talked about the generative finite state automatas. Any finite state automata could behave as a generative ones. Okay, these two are equivalent, and one of them is ambiguous. This one is ambiguous, this one is not. This one is deterministic, this one is not deterministic. This is deterministic. This one is not deterministic. Okay, why do we call this deterministic? Because for a single input, there is only one path to follow. For this one, there might be more than one path, and you are supposed to explore all the paths possible. Ali Haydar says that there is no either. Why don't you guys ask your questions using your microphone? I don't have to go back and read that one. I don't know when you asked that, Ali Haydar. I don't remember. So I'm not going to answer that. There was a table. I think there was an E in there, and if you don't use microphone, I mean, I'm skipping your questions. Okay, so determinism and non-determinism is something that we are going to use. Deterministic ones are easy to handle because we have a very nice algorithm there. Non-deterministic ones, we like non-deterministic ones because they are so powerful to use. I mean, writing non-deterministic finite state automata is more convenient than deterministic ones. And this is another way of building non-deterministic finite state automata using epsilon rules. Epsilon means that you can, if you are at Q3, you can go back to Q2 without receiving any input. You don't have to get an input to go to Q2 from Q3. To go to Q4, you definitely need an exclamation mark, but to go back to Q2, you don't need any input. Another non-determinism example. Okay. This is a very important information. Non-deterministic machines can be converted to deterministic ones with a fairly simple construction. Okay, so that means that they have the same power. I mean, by comparing these two, this is deterministic. There is only a single path, and that there might be more than one path with the non-deterministic finite state automata. But power-wise, I mean, there is no language that can be expressed by a non-deterministic finite state automata that cannot be expressed by a deterministic one. So one is not powerful than the other. Remember what I said? We like this one because they are powerful to express stuff. It is powerful for us human beings. Sometimes we use them to explain something in a shorter, smaller finite state automata. Okay, so for humans, we don't like to deal with finite state automata with hundreds of nodes. Maybe 10-15 nodes is good enough for us. With the non-deterministic finite state automata, sometimes we can achieve it. So it is powerful for us. It is easy for us to explain some of the languages, but they are equivalent. Deterministic and non-deterministic ones, they don't have any advantage or disadvantages in terms of expressibility. Okay. Okay. For the non-deterministic recognition, so what does that mean? If there is a conversion possible between non-deterministic to deterministic one, if I have a non-deterministic machine available, and if I have an input, how do I know that this non-deterministic machine, non-deterministic language is, or finite state automata can recognize this string? I can convert this non-deterministic machine to a deterministic one and execute our derecognize. Okay, I can do that. The book says that you can do a state space search. Maybe I should just show one example here. I have exactly the same example that I showed you, maybe BAAA exclamation mark and end of word. So I started from here, tape Q0, When I received B, there is nowhere to go but only Q1. When I received E, I need to go to Q2. When I received E, there could be two positions, either Q3 or Q2. This one chose to Q3. After that, after Q3, okay, after I go to Q3 and now I received another A, this didn't go anywhere, right? This just said this is wrong because I am receiving an A at Q3, I am receiving an A, and it doesn't go anywhere. That means that I need to back up. I am backing up now, I am trying Q2 now. I went to Q2 and I received another A. Now I am going to Q3. I could have stayed at Q2 here. Okay, that was another possibility. Now I am at Q3 and this is exclamation point. Now I am done and I am at the final state. So this is a state space search. It chooses this path and you start from the start, you ended in a final state and you're done. It's a state space search. Either you could do this kind of a search or you can convert your grammar, you can convert your finite state automata to a deterministic finite state automata. Okay, so I'm not going to talk much about how to convert a non-deterministic finite state automata to a deterministic one, but it is possible and I'm sure some of you already know this. Okay, again, same question, why bother? Non-determinism doesn't get us more formal power and it causes headaches, so why bother? Why bother? Because it is more natural for us to find solutions with the non-deterministic finite state automata. And we are going to see in a few minutes. Let's say I have this finite state automata 1 and another finite state automata. Okay? Let's say this is sheep language and this is chicken language. And I like to build a new language that is composed of sheep words and chicken words. So I'm going to take the union of it. So what do? I put finite state automata 1 here, finite state automata 2 here, okay? And I make a new start state, a new end state, and I connect them with the epsilon transitions. See, using the non-deterministic finite state automata techniques, I made a union of two finite state automatas. I know that this is non-deterministic because there are epsilon transitions. Okay, there are epsilon transitions. And I know that if I try hard, I can convert this whole thing to a deterministic finite state automata. This is possible. Other than union, what could I do? Concatenation, okay? After the first finite state automata, I like to continue with the second finite state automata. So it's going to be a sheep word, after that a chicken word, okay? Something like that. This is a concatenation. Again, a transition. Okay? Negation, for the negation, let's say I have a finite state automata, 1. It recognizes some words. I like to build a finite state automata, okay, that accepts all the rejected strings of this finite state automata. And it rejects all the accepted strings of this finite state automata, just the opposite. Okay, this is how you do it. Construct a machine M2 to accept all the strings not accepted by machine M1 and reject the strings accepted by M1. So this is the way. Invert all the accept and not accept states in M1. So let's say this is Q0 start state. A, this is Q1 and and B, and this is my Q2. Let's say this is our final state. So this is a very simple language. It accepts A, B. That's it. Nothing else. Okay, let's say my alphabet is only A and B. It doesn't accept A, right? It doesn't accept B. Okay. It doesn't accept B and A, and etc. So what should I do? So what it says that, okay, do this. Invert all the accept and not accept states in M1. So I am going to do this then. Q0 will be accept, right? Q1 will be accept, and Q2 will not be an accept. What else? Also, as one of you has suggested, there should be an invalid state to go to, and that invalid state is going to accept everything. I step, and all the rest is going to go there. So this is A, B, and these are all the rest. This is B and A, and this is going to be an accept state too. So if I just do an A, it will be accepted. If I just do a B, it will be accepted. BA will be accepted, but A and B will not be accepted because it goes there. So this is negation. This is negation. What did we do now? Finite state automata 1 union finite state automata 2. We did that, right? We did F1 plus concatenation F2. Also we did F1. So what does this tell you? If I have all of these, how about this one? How about this one? F1 union F2. What does this do? It says F1 intersection F2, not, right? So using the not operation and the union operation, I could do the intersection of two finite state automata. Okay, like that. Okay, let's say F1 is my sheep language and F2 is my chicken language. If I like to build the intersection of these two languages, only recognize that is words that is common to sheep and chicken languages, what do? I take the negation of F1, union, negation of F2, and take the negation of it. It will be equivalent to F1 intersection F2. Okay. So as I said, to be able to do concatenation or the union or the intersection, it is very useful to have epsilon transitions which are valid in the non-deterministic automata. For us human beings, they are very convenient, but for computers there is no difference between in terms of expressibility between finite state automata, deterministic finite state automata, and the non-deterministic finite state automata. Okay, good. Any questions? Now we have this finite state automata thing going on. Let's go to our regular languages like the English and Turkish. Let's look at them. Okay. But before we do that, let me, oh no, okay. Before we do that, let me give you a few definitions. Okay. About words and tokenization. Sometimes these will be useful for us. There are a few pointers. Okay. After we tokenize the words, maybe we are going to do the morphological analysis, normalization. Most of the NLP tasks before we do anything, okay, we need to find the words, okay, we need to find the words. Sometimes finding the words may not be that easy for some languages especially. So, every NLP task needs to do some text normalization. Segmenting, tokenizing the words in the learning text. Normalizing word formats. For example, these are all the same word, same verb, right? We need to normalize them. Okay, we need to make them the same. Okay, normalize. And sometimes we need to segment the sentences so that I know the border between the sentences. I am going to introduce you a few techniques for doing each of these. Okay. Sometimes doing this very difficult, especially for the spoken language. When I talk in English or Turkish, I most of the time say o, ü, those kind of filler nonsense sounds. For example, this guy, I do mainly business data processing. This main doesn't have any meanings. This doesn't mean anything. But we humans use those kind of stuff when we talk. Okay? So for the spoken languages, finding the words and counting them is not that easy. Even for the written ones, okay? This cat and cats, they are the same stuff, okay? Their lemma is the same. Same stem, same root, same aynı kök, same part of speech. Rough word is the same. Rough word sense is the same. They have the same lemma, but we need to find this kind of case. We need to know cat and cats are the same thing. Okay? Cat and cats are the same thing. Word form, on the other hand, the full inflected surface form, is what we see on a text document. Okay? Cat and cats are two different word forms or tokens. Their lemma is the same, but their word forms are different. Their tokens are different. When we count the words, are we counting lemmas or are we counting word forms? Okay? Sometimes this makes a difference and we should be careful about it. So, how many words are there in this red sentence? They lay back on the San Francisco grass and looked at the stars and the year. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. It looks like there are 15 words, but is San Francisco a single word or? Because, I mean, it is always, nobody calls it San, nobody calls it Francisco, right? It is San Francisco, is it a single word or multiple words? And it changes from language to language. We don't know, okay? So, how many types? What was the type again? Type, okay? Type is an element of the vocabulary. Type is the element of the vocabulary. That means type is the one that you see in a dictionary. Okay, so there are 13 types. Why there are 13? Because I have the and the, okay, these are the same type. What else? They lay back. Okay, there are 13 types, and if you ignore that San Francisco thing, but the number of tokens is 15 because this token and this token, they happen in different places. Okay, when you say the word count, WC minus C, it counts the tokens, count of words. It counts the tokens. Okay, so don't forget this word form lemma, type, and token are some definitions that I am showing you right now. And when we look at some of the corpora means that it's a large text resource, text database, if you like to call it that way. And when we say how many words in that corpora, we usually count the number of tokens and number of vocabulary. Okay, number of tokens and number of types. Okay, for Shakespeare dataset, all the works written by Shakespeare, okay, if you put that in a text file, there are total of 884,000 tokens. But Shakespeare totally used, okay, 31,000 types. In his dictionary, in Shakespeare's dictionary, there are 31,000 words. Okay. There is another data set. It's called switchboard phone conversation. Somebody collected all these phone conversations and transcribed them. It has 4.4 million tokens, but the number of types or the vocabulary is just 20,000. See, Shakespeare is using 50% more types. He did not talk that much. Still, so he knows many more words, right? Google Ngrams is a data set where Google collected by scanning all the printed text. They say that they have a total of 13 million words. Do you think there are 13 million words in this world, English words? No, but Google says that, okay, this is a word. Okay, this is a word too. Okay, so if you count all the names of the proper names and the names of the villages and the cities and the rivers and the mountains and everything, also this is a word. The Google says that this is a word type. Okay, Google also says that this is a word too. If you do all of that, then you reach like 13 million word types. And this number is a very big number, as you see, 1 trillion. I am not talking about billion. We are talking about trillion. Okay. Trillion is what? 10 to the power 12. Is that correct? 10 to the power 9 is billion. This is trillion. It's a very, very large data set, very, very large corpora. Because they say that this is all the English that we know. All the printed English. Okay? This is how you... Okay, how about this one? Number of words types is usually comparable to square root of the number of tokens in a data set. Okay? So this is good. Of course, this is not valid. I mean, what is the square root of 2.4? I mean, it is larger, but it doesn't tell me equals or something like that, okay? So this is just a comparison. Number of words types in the dictionary is going to be much smaller than the number of tokens. Good. Let's look at this Unix tools and do some simple tokenization. We are going to tokenize a given text file. Using this tr. Tr does that. Tr, okay. Tr is translate or delete characters. That's the Unix command. It says that whenever you see anything other than these characters, from A to Z to A to Z, small case and uppercase, replace them with a new line. Okay. Minus S and minus C means minus S is squeeze repeats. If you are repeating some characters, just many spaces, just squeeze them. C is the complement, just the opposite. Anything opposite of these letters, you replace them with a \n. And as an input, I am going to give you Shakespeare.txt. Then after that, each word is going to be sorted. Then you know this one, unique. Unique is it doesn't list the same word twice, and with the C it will give you the count. So if I do that, it tells me that the word A happened 1945 times. Aaron happened 72 times. Okay. Well, it looks like uppercase Aaron and lowercase Aaron is kind of different. So it is counting them separately. Maybe you should deal with them. So we are doing some tokenization, and we assume that words are separated by anything that is not within these ranges. Okay. So I think this is just breaking up. Let's look at this first part. Okay, let's look at this first part. Okay, these are the words. And after the sort, I have this. And after the unique, I have this. Oh, look at that one. It says that replace all the uppercase letters with the lowercase letters and do exactly the same thing. First, replace all the uppercase with the lowercase. So everything is uppercase, lowercase now. Then do all of that. Okay. So this is one way of tokenizing your data set. Very simple. But the assumption is anything other than the letters, anything other than the range, the here and there, is considered to be separating the words. Okay, but that may not be true because is Finland's one word or two words? I mean, in that case, it's going to count as two words. What are I am isn't, are these one word or two words? Okay, what are I am is not. Is Hewlett Packard two words or one word? State of the art like that. Okay, so these are the issues in this tokenization. I didn't do a very good job, but it does something for me. Sometimes the things are very different for different languages. Does any of you know German? With the German noun compounds, okay, noun compounds, isim tamlamaları, they don't have any spaces between them. Lebensversicherung, Versicherungsgeselle, Gesellschaftsangestellte. I can't read it. I think Lebens is a word. Versicherung is a word. No. Is a word. Gesellschaft is a word. Sangesteller. I think 1, 2, 3, 4 words in there, and there is no space between them. Again, tokenization will not work with this one. Doesn't work. Some languages, Chinese and Japanese, believe or not, they don't have spaces. They don't have spaces. They don't need this large space bar on their keyboard. All they do is they just write their letters or words one after the other. Okay. And tokenization becomes a problem in there. Okay. So they just read it, but their words are not separated with spaces. And sometimes in Japanese, they use certain alphabet, katakana, then other alphabet, then other alphabet. Sometimes they use Latin letters, Roman letters, and etc. Okay. So it is more complicated for these kind of languages to have tokens. Okay. Any questions so far? What would have been the situation if we didn't have the spaces in Turkish? If we don't have the space in Turkish, our life would have been more difficult, or wouldn't make any difference? But it looks like it doesn't make any difference for the Japanese or Chinese. Okay, you think about it, and we will continue when we come back. We will be here at 16:03.
Paralı olmaz. Paralı olmaz da belki şu şeyin program açılırsa arşiv eder ya. Yönetimleri falan şöyle oraya dinleriz. Oradan bir ders alırız.
Geç olmadan bir sorun da vakıf üniversitelerinden bir yerden bir ders alsın. Evet. Parası bozsun.
Parayı nasıl iş yapıyor? Sayacak mısın?
Biz sayacağız evet. Parasını veriyoruz. Hemen şimdi arasın. Hemen şimdi arasın. Hatta işletmeden bile alabilir belki onların şey dersi varsa.
Onlarda var mı böyle iş yönetimi falan?
Evet. Akşam ders veriyorlar onu. Evet. Ulan niye aklıma geldi? Okay, I am back. So, tell me what would happen if Turkish didn't have space. Just open up a Turkish, let's say Google News. Okay, let's not go into politics and go to some sports stuff. I'm going to copy some text and we will try to, what kind of, okay, just clickbait and put it in a notepad, right? File new and Control H, replace all the spaces with nothing. Okay. Erol Bulut yönetiminde İzmir ekibiyle karşıya gelen sarı lacivertliler sahadan 3-2 galip payı. Sometimes it looks like I'm picking another word like İzmir ekibiyle instead rakibiyle karşı it looks like it is another word. Nin gollerini Guilherme kaydetti. It looks like I don't have that much problem. That there would be some ambiguities. Koltuğuna oturdu. Liderlik koltuğuna veliderlik sometimes there might be ambiguity, so we need space. These languages, of course, they are fine without the space. And it looks like what they do is they have this word segmentation algorithm and it works very, very good. So this is what they do. In Chinese, words are composed of characters. Characters are generally one syllable or one morpheme. Syllable is hece. Okay. Average word is 2
Sorry, you got muted.
So you did not see anything you did not hear anything that I told you? So nobody's listening? I was talking about... Okay, never mind. Okay, Chinese...
You got muted 5 seconds ago.
Oh, really? Somebody muted me. Oh, okay. So I thought... I thought you missed the whole Turkish part. Somebody muted me. Chinese, they do this. Standard baseline algorithm, they also the greedy algorithm, it works very good. It just given a word list in Chinese and a string, okay, start from the beginning and find the longest word in the dictionary that matches the string starting at pointer. Okay, so at the beginning you find the longest word that matches, and then that's your word. Then you find another word, and it works very well for Chinese. Okay, it looks like it doesn't work very well for the English. The cat in the hat, if you put them together, the cat in the hat, it becomes the cat in the hat. But the table down there, theta bled on there, you may be confused with other words. The table down there and the theta bled on there are, without the spaces, are exactly the same thing. Doesn't generally work in English. Okay, good. And it works astonishingly well in Chinese. Each language has its own easy and difficult parts for the tokenization or morphological analysis or the syntax analysis, and we try to point them from time to time. Okay, let's look at the normalization. Sometimes when we have a text, we like to normalize it. For example, we like to match USA with USA, either written this way or that way. Okay, this is important for information retrieval. If somebody asks us what is the population of USA, okay, either say that way or that way. We need the normalized terms, okay? We need the normalized terms. So we can do this by either using some rules, or we implicitly define equivalence classes saying that this word and this word are equal, okay? Or we are going to ignore all the periods in a term, kind of like that. Okay, case folding, another case of normalization. Uppercase and lowercase, remember the solution that remember the thing that we have used for the Unix example. We converted all the uppercase letters to lowercase letters. Sometimes it doesn't work very well because fed is a proper name. Fed is the past tense of feed. Okay, that capital is important there. US is United States. This is us, right? So sometimes case folding, uppercase, lowercase, introduces some problems during the normalization. So these are some problems specified for the English. Lemmatization, lemma, remember we talked about the lemma, the kind of the stem of the root of the words, okay? We like to see M, R is all to be B. Cars, all they belong to this equivalence class car, okay? If somebody types this for information retrieval, we convert them to the boy. The boy's cars are different colors. The boy car be a different color. Okay. So you are not going to find, okay, cars or cars with the apostrophe in the dictionary, right? All you're gonna find is this car, or you're not going to find R or is in the dictionary. All you find is B. Okay. Lemmatization is the find the correct dictionary head word form. Okay, find the correct dictionary head word form. Sometimes it is not that easy. For example, for Turkish, it's a very classical example. Masalı. How do you find the lemmatization? How do you lemmatize this one? How do you find the head word of this word? Is it masal or is it masa? Right? There is you cannot by looking at just this word only, you cannot make a decision. And another example from Spanish, This word in Spanish, I want, and you want, they have the same lemma. Want. Their lemmas are the same. So if you do that kind of lemmatization, you are losing some information. And sometimes it is not that possible. Masal and masa has nothing to do with each other. They are not related. But by coincidence, the ambiguity makes this lemmatization difficult. Okay. Another issue with the tokenization, okay, is the morphology. Morphe means that it's like syllable, like hece. But it is more meaningful than hece. The small meaningful units that make up words. Okay. A word is composed of the stem, kök, and affix, ek. Okay. This is kök in Turkish and ek. The core meaning bearing unit is the stem, and affixes, bits and pieces that adhere to the stems. It could be prefix or postfix, before the stem or after the stem. They are all called affixes. Okay, they are often with grammatical functions, inflectional, derivational affixes. We are gonna see some examples later. Okay, given a text, finding the stems of the words is important. Okay, finding the stems of the words is important. Stem is a little bit different than lemmatization. Lemmatization is how to find the correct dictionary head word. Okay, so the lemmas of these words are B, but stem is a little bit different. Okay, so there is an algorithm, very crude algorithm from 1960s for English that finds the stems of the word. It doesn't work perfectly. It overdoes it. Sometimes it does it wrong. Give this sentence and you get this out. For example, compressed and compression are both accepted as equivalent to compress. If I give this, the stem for is for. For example, it is example without the E. Compressed is compress, and is and, compression is compress, R is AR, both is both, accepted is accept, etc. So let's look at this. Stemming algorithm. It's a simple algorithm. Okay, Porter's algorithm. 1, 2, 3, 4 steps. Let's say 3 steps. 1 step, 2, and 3 steps. It says that these are the rules. These are rule-based thing. All the SS, ESS is converted to SS. So caresses, cares. All the IES at the end of the words are just I. Pani is to pani. All the SS's end of the words are SS's. Okay. And all the S's at the end of the words are just gone now. All the words ending with ing that involves a vowel. Vowel means sesli harf. Okay. Okay. They are all gone. Okay. You just, if it's walking, see, walking. Since there is a vowel in here, A, I get rid of this one. So it becomes walk. Okay. But I don't touch sing because inside the sing, there is no vowel, there is no S. I mean, inside S, there is no vowel. Again, if there is an ed at the end of the word and there is a vowel in the rest, then I get rid of ed. Plastered, plaster. So it's a simple English stammer. Step number 2, all these kind of international kind of stuff, international kind of, replace them with 8. Relational, relate. International, internate, kind of. and either eyes, digitizer, digitize, ater, ate, operator, operate. Okay. For longer stems, you're gonna do this revival, revive, adjustable, adjust, activate, active, and there is no E in E afterwards. Kind of normalized. Okay. And this rule is a simple rule that I'm not going to talk about it. I'm not going to much talk about this. I already talked. Well, maybe, okay. So they have implemented this rule like this. Get the Shakespeare, grab, you know what this is? Find all the words that end with an ing, right? If you know how to use grep. Find all the words that end with ing, sort them, make them unique. What is the difference between this one and this one? I am waiting. I am waiting. If nobody answers, I will pick a random one. I am going to pick a random person.
Can I answer the question?
Sure, yeah.
It's in reverse.
R is reverse. How about N?
Number, numeric.
Yeah, numeric. Numerical sort and reverse. Okay. So find all the words that end in ing, sort them and unique them with the counts, and sort them reverse. So king, being, nothing, king, bring, like that. Okay. So I want this rule to be executed on this one, right? Maybe, okay, like that. Okay, good. What? No, oh, okay. So, how did it work? Say that instead of doing this, get this one. This time it doesn't say grab all the INGs. It says grab all the words that end in ing, but before ing, they should have these vowels, right? A, E, I, O, and U, vowels. They should include vowels. And sort and unique and sort. And I get these. So it looks like this is nice. Being is going to be be. Coming is going to be come. Having is going to be have. Loving is going to be love. But the others are meaningless. Nothing is going to be not, right? This is going to be NOTH. So this rule works somehow to a degree. It doesn't do a very good job. Okay. So we never said that this Porter's algorithm is a perfect algorithm. It does some kind of a job. Okay. Good. So stemming is, I mean, you could find those kind of rules for certain languages, but for certain languages like Turkish, finding stemming rules that works like 80% of the time is not possible. This is a very famous Turkish example. Uygarlaştıramadıklarımızdanmışsınızcasına. I cannot read it. And this is the English corresponding sentence. Behaving as if you are among those whom we could not civilize. And morphological analysis says that, okay, this is the stem, okay, uygar, and the lash is becoming, it's the cows and not able and past tense. plural, and person one plural. This is ABL done. I don't know what that is. Past tense again. Second person as if. So how many morphological affixes I have? 1, 2, 3, 4, 5, more than 10, right? And each one is adding one after the other. So it doesn't look like you are going to have this kind of a 1, 2, 3, 4 rule set to take care of all these kind of complexities of language like Turkish. Okay. And for this, we are going to develop some techniques later, and they are not going to be perfect, but Turkish has more work to do with in terms of morphology. Okay. But I forgot to change it to... Okay, good. So that was word tokenization. Let's talk a little bit about sentence segmentation. Okay. For the word tokenization or the morphological analysis, I told you some techniques and the problems. The same problems or similar problems exist for the sentence segmentation. How do you separate two sentences? You might say that period is end of the sentence, but sometimes question marks or the exclamation marks are the end of the sentences. And if you say periods are end of sentences, how about this? Abbreviations, right? Inc. Incorporated, doctor, like numbers, right? In Turkish, you would say üçüncü sınıf, right? This is not end of the sentence. Okay, we use it. So how do I make the decision that this is the end of the sentence? You may come up with a handwritten rules, okay, or some regular expressions, or sometimes we use machine learning techniques. And let's look at some of them. This is one decision tree, a hand-built decision tree. Okay. Let's say it's a dot. I found a dot, and I'm asking this question. Are there lots of blank lines after me? If there are some blank lines, then this is end of sentence. If final punctuation is okay, question mark, exclamation mark, or column, okay, then again it's end of sentence. If the final punctuation is period, after that there is no letters or anything other than sentences, then I need to look at this. I am etc. or other abbreviation, like we could say etc. dot, right? If I am not this, then it is end of sentence. Otherwise, it is not end of sentence. So this is a decision tree that makes a decision on end of sentenceness. Doesn't work all the time, but it's a rule-based method. And it will be different for Turkish and English or other languages. Okay?
Can I ask a question?
Sure.
What do we mean by the lots of blank lines? Why it's not fixed?
Well, I mean, lots of means that more than one. They try to make it kind of informal. See, this is determining if a word is end of sentence. I am a word and I am asking this question. After me, are there lots of blank lines? More than one line? Yeah, okay, you are end of sentence. Okay. This is not a complete rule set. Just an example to make it more interesting. And it just says that etc. or other abbreviations. I mean, it is not talking about everything. Just giving me an example. You could have put a number in there, like more than 1, more than 2, etc. Okay, more sophisticated decision tree features. These are features, right? Counting the number of lines, looking at the punctuation, okay, looking at the word or other more complicated features, okay. Case of word with, if I have a word with a dot, with a period, I may look at it, is it a uppercase word, lowercase word, or a capitalized word? I mean, this is an uppercase word. This is a capitalized word, and this is a lowercase word, and this is a number. A period at the end of these words might mean different. Okay, case of the word after period, then, I mean, after the period, if you start with a capital or small case, right, then I'm gonna behave differently. These are some features, okay, and also there are some numeric features: length of word with dot, probability of the word with dot, okay, probability of the word beginning of the sentence, etc. So these are other numeric features. How would you calculate this one? Probability word with period occurs at end of sentence. How would you calculate that one?
By the datasets.
You have a data set. In your data set, you have 1,000, 100,000 sentences. You know which words occurs at the end of the sentence most often. And the word that you are looking at is a is a probable word, then you will say that, okay, this might be an end of sentence. Okay. Okay. So that's one way of doing it. Okay. So this is a decision tree. How do you do the decision trees? You find these kind of features. What should I look at? Okay. The blank lines after the word, final punctuation is etc. and etc. The probabilities, uppercase, lowercase, capitalized numbers, etc. You find all those kind of features. Let's say you have 100 features. One of them is blank lines after. The other one is probability of and of sentence. The other one is length, etc. I have 100 features, and I like to build a decision tree like that to segment the sentences. Okay, but the thing is that how am I gonna find the first question at the top? Okay, how am I gonna find the first question at the top? For that, there are decision tree building algorithms. They use information theory, they use entropy. They say that if you ask this question first, your decision tree will be shorter. You don't have to ask many questions. This will be the most interesting one. Okay. Decision trees are not always the same, are not always the only solution for us. There are other ways of doing it, like the logistic regression, support vector machines, or the neural nets. Okay, and we are going to look at some of them later. Okay, now we looked at word tokenization. We looked at the definition of tokens, lemmatization, okay, normalization, word stemming, morphology and affixes, Okay, these are some terminology that you need to know, but you might think that I have never given you a solid algorithm that works for everything. That's probably usually rule-based stuff or easy to explain stuff doesn't work for all the cases. All I'm doing is showing you how the ambiguity is spread out in all of the word level NLP tasks. There are many places for ambiguity. There are many places for solutions for the resolving ambiguity, and unfortunately we are not going to be successful for all the languages using the same algorithm. Different languages require different kind of algorithms for the lemmatization and the stemming and affixes. For Turkish, none of them will work at a satisfactory level. You need to do the full morphological analysis to find the stem of the word. Okay, so that's why let's look at this morphology more carefully. Now I'm gonna start a new topic that deals with the morphology. Let me find it. Okay, this one is going to be about morphology, and we are going to use finite state machines to do the morphology. Well, it says that we are going to talk mostly about English morphology, but I am going to introduce concepts from Turkish morphology too, and we're going to look at a few papers. In fact, let me give you a paper so that you read that paper for next week's class. Let me find the paper. Where is the paper? Here's the paper. Yeah. Can I send this paper to you using attachment? There is an attachment here. Oh, okay, good. This is a classical paper. So I send it using the chat window. Turkish morph paper. Okay, there is a PDF document. Did you get the document? Okay. I want you to read that paper. You don't have to understand everything, okay? But then at the end of this chapter, we are going to look at that paper. It's a very, very old paper, but it kind of tells us. Well, it says gönderilemedi. I don't know why. Why? Yeniden dene.
Actually, I can see the paper.
You see it?
Yes.
You can you download it?
Actually,
I can open it. It's no problem.
Oh, okay. So for some reason it says that gönderilemedi. Anyway, so read that paper. We are going to look
Where
at
did you send it?
what?
Where did you send it? I can't see the link.
There is no link. I just sent the whole PDF document.
Oh. All right, I will find it eventually.
Okay. Just a minute, I need to take this phone call. Excuse me. Efendim hocam. Şükür iyilik, sağlık hocam. Sizler nasılsınız? Yo, bana bir şey gelmedi. Neyle gönderecekti? Ha, maille mi gönderdi? Ya ben şu anda dersteyim de yani son 2 saattir bakamadım e-maillerime. Vallahi yok ya, ben onu almadım, yok ya. Tabii yok, hafta sonunda baktım. Ben sadece son 2-3 saat içerisinde bakmadım. Bir dakika, ben şimdi şeyden bir bakayım da bir şeye falan mı takıldı acaba? Sivas.edu'den geliyor değil mi? Sivas Edu TR'den geliyor, doğru mu? Ha, bir dakika, tamam. Bugün saat 14.59'da yollanmış. Bir dakika. Tablo diyor ama hocam ondan önce bana yok yani Kadir Ali Seçer'den gelmiş. Bugün gönderilen bir şey. Sadece bir Excel bunlar. Ondan önce bana Sivas şeyden gelen sizin e-mailiniz var. En son çarşamba gelen var. Ondan Semra Şahin'in var. Kadir Ali Seçe'den bana başka bir e-mail gelmemiş. Evet. Eğer, uh, kaç kişi var? Tamam, çok değilmiş. Vallahi bugün alabilirsem akşam hemen bakmaya başlayalım, geç kalmasın. Olmazsa şey yapsın, WeTransfer falan yapsın. Yani bir yere koysun, linkini yollasın. E-mail'le belki büyükse gelmiyordur. Bir yere bir link koysun, linkini bana yollasın. Hı. Evet. Aha. Oldu inşallah, bekliyoruz. İyi çalışmalar. Okay, so we are going to look at English morphology, and we are going to look at finite state automata, a variation of finite state automata, to deal with this kind of stuff. Okay, so the words we talked about it, words, how do you count the words? I am not going
Your mic is muted.
Okay. So words are there. We already talked about them, including the lemmatization, normalization, and etc. Let me get rid of these annotations. Okay. I am not going to go into details of these words again. We talked about stems and affixes and etc. So English morphology, like Turkish morphology, we can analyze it. We can study it in two ways. One is inflectional morphology. The other one is derivational. It's like this one is türetme ekleri, çekim ekleri. Inflectional morphology and derivational morphology. For Turkish, both of them are very complicated. For English, inflectional morphology is very simple, especially for the nouns, right? For the nouns, if I have a book, noun book, okay. For the inflectional morphology, all I can do is box. That's it, right? But for Turkish, for the inflectional morphology, if you say kitap, for the çekim ekleri, you could say kitabı, kitaba, kitapta, kitaptan, okay, and kitabım, kitabın, kitabımız, etc. How many of them here? Like hundreds of them. Okay. Total in the inflectional case for the Turkish, they say that there are a total of 2,500 inflectional forms against the English one or two forms. Okay. So inflectional morphology for Turkish is difficult, is complicated. For English, it is much easier. Derivational. When you come to derivational morphology, it is again difficult for Turkish, complicated for Turkish. For English, it is more difficult than the inflectional ones, and we are gonna see, especially for the verbs. When you have the verb, for example, again, book word, there is booking, there is booked, right? There is, for example, booker. When you say er, it's booker, and with the certain other kinds of verbs, if you put other suffixes, if you put other affixes, you will get other verbs, or you will get other nouns, and we are going to see some of them. Okay, so usually for all the languages, nouns and verbs are two main categories of the words. Okay, nouns and verbs, isimler ve fiiller. Okay, of course there are many other classes of words, but nouns and verbs are common for all languages. Okay, and it changes from language to language. Okay, for now, since we are only interested in word stems and the affixes, these two classes are just enough for us. Okay, inflectional morphology, as I said before, it has the same word class. Okay, many forms of the word, but they all have the same word class. And why do we have inflectional affixes? Because it serves as a grammatical semantic purpose. It looks different from the original, but meaning-wise it is almost the same thing. Okay, in nouns, inflectional morphology very simple, and verbs are a little bit more complex in terms of inflectional morphology. Of course, we are not counting the irregular verbs in irregular nouns and irregular inflectional stuff. For example, when I say book and box, that's simple. For mouse, it is not mouses, it is mice. For goose, it is geese. For ox, it is oxen, right? Again, for the past tense of the verbs, for go, it is not goed, it is went. Fly, flew, right? So English is difficult in terms of irregular inflectional morphology rules, and these irregular rules are the more common rules. Okay. For the regulars, everything is fine. Walk, walks, walking, walked, walked again. Okay, these are inflectional forms of the verbs. Again, for the irregulars, eat, eats, eating, and the past tense ate, eaten, catch, catches, catching, quote and quote. Again, for irregular verbs, we need to be more careful. Okay, so inflectional morphology in English is straightforward. The only complicated part is the irregular ones. Those are all exceptions. Okay, derivational morphology in English is more complicated. It's not as complicated as Turkish. Well, maybe it is as complicated, but it is much more complicated than the inflectional morphology. Okay, when we say derivational morphology, we mean that the meaning of the word changes when you do this kind of morphology. Okay, examples. For example, computerized, computerization. This suffix, okay, this affix or suffix, when you add it to computerize, it becomes computerization. When you do this e, appointee, appointee, okay? Kill, killer, fuzzy, fuzziness. So the meaning changes and you get a new word, and these are called derivational examples. Derivational examples. And they are more complicated. They are the number of rules for these kind of affixes is many, and there are many irregularities too. For example, this e, kill, is a verb. When you put er at the end, it becomes a noun, killer. Appoint is a word. Okay, when you say add e, it becomes a noun. But you cannot put an e like kill e. You cannot say kill e. Killer is okay, but kill e is not okay. Appoint e is okay, but appointer is okay too, right? So not all the suffixes work with all the words. There are many irregularities. There are many exceptions. Okay, so these are verbs and adjectives to noun. From verbs to nouns, or from adjective to nouns, fuzzy, fuzziness, good, goodness, bad, badness, right? These are all, NESS is a affix to convert from a adjective to noun or verb to noun. Okay, nouns and verbs to adjectives. Computation is a noun. Okay, computational is adjective. Okay, embrace is a noun, embraceable is a embrace is a verb, embraceable is a adjective. Okay, so these are some derivational examples, and many paths are possible. Computer, computerized, computerization. Computer, computerized, computerizable. And you can do the you can apply the same rule more than once on the same stem. Okay, so the derivational morphology in English is much more complicated than inflectional morphology. So we are going to use the same tools to deal with the derivational morphology. Okay, let's look at this again. Finite state automatas. Okay, but it looks like I am out of time. I am 3 hours now. I think I will continue on this next week. But before I say I am done, let's look at this one. Derivational rules. You start with a noun, you put an "is" at the end. Computer, computerize, computerization, right? What else can we okay? Drive, derivation, derivative, and derivativeness, derivatively. How about this one? Compute, computable, computabulation, computabulation. Do I have such a word as computabulation? Computabler. How about this one? Likeable, likeabler. How about this one? Is there such a word, likeabler? Compute eyes. Computer.
The arrow is other way around.
Compute, computerize, computerizer. It works from there to there. Oh, okay. I'm not. Oh, okay. The arrow is the other way. Okay. Computer, compute, computerize, computerizable, and computerizableness, computerizability. So this is as you see, this is a finite state automata, and they have derived this one. The paper that I gave you, Turkish Morphology paper. Let me open this. It has rules like that for Turkish. Let me show you a finite state machine. Where is it? Oh, okay, here it is. These are the verbs. And before coming to verbs, the nouns are easier usually. Let's look at these. Okay, noun. Nominal root. This is A is lash, leş. Okay. Okay. Kötü, kötüleş. Verbal root. Kötüleşmek. Kötü is an adjective. When you do kötüleş, it becomes a verb. Kötülen, iyilen, iyilenmek. See, this one, lar, ler. This capital A is A and E. Okay. Capital H is I and Ü and U, kind of. İyi, iyilik, kötü, kötülük, etc. İyi, iyici, küçük, küçücük, kind of. These are those kind of rules. So, as you see, this in the finite state machine here, there are except states, and before that, I go to many transitions, and with this transition, I can make an analysis of the given word. And these are for nominal nouns and adjectives again. Somebody had a question?
Yes. Is this finite state machine deterministic? Because I couldn't find any inputs that lead to two separate nodes.
Well, I don't think that it is deterministic. It is designed to be understandable. I don't think that it is deterministic. If you look harder, you're gonna find cases where it can happen that or that. It is definitely it is definitely not deterministic, because using this finite state machine, we will do stuff like, where is my masal? Masal is from this paper. Oh, I cannot find it. Well, I mean, there were some examples that shows different. Okay, here it is maybe. Okay, görülemiyormuşum. That's single thing. I like to show you. Okay, maybe just go to. There is a short version of it. Very short. Version of it, and in that short version, it's a poster version. Okay, here it is. Did I find? Okay, good. This is good. Okay. So, çalışmanın has two different parses. One meaning is of your work, çalışmanın, senin çalışmanın. The other one is of the work, sabah yapılan çalışmanın. Okay. The same finite state machine produces this one and this one. Çocuğu let's look at this one. Alınmış. How many different parses are there? 1, 2, 3, 4, 5, 6, 7. Alınmış. It was your red one. What? Oh, okay. You understand what it means? It was your red one. Kırmızınmış yani. Okay. The other one is it belongs to the red. Kırmızınınmış. It was a forehead. Adamın alnıymış gibi. Satın alınmış. Alınmış, evden alınmış. Birisi offend olmuş. Offended person. See, they are all different parses of the same word and the same finite state automata is used to parse all of them. Okay?
Okay. When we can generate words, we can generate multiple words from the branches, but when we know the inputs and we want to check if the inputs complies to the rules, isn't that what deterministic means? Like there can be two rules, like there's two possibilities, like and I will know if the possibility is that or not that after I enter them.
By looking at a single word in any natural language, you won't be able to know which parse is valid, or we won't be able to know which of these are valid, okay? So the morphological analyzer finite state machine's responsibility is first to tell you that this is a valid word, okay, morphologically valid word. That's the first thing. The second thing is it should give you all possible analysis of the word, morphological analysis of the word. If you like to know which one is the intended morphological analysis, morphological structure, then you need to look at the context. Without looking at the context, you won't be able to know which one it is. So by definition, your finite state automata should be non-deterministic because it should produce many different paths to accept a string. Okay? Okay, so just look at this paper, try to understand it, but don't try to understand the details because there are many words that you don't know the meanings of. And at the end of this chapter, I will show you some English examples and we're going to look at the Turkish corresponding parts in that paper. Okay, that's it for today. I am going to see you next week.